Welcome, listeners, again to our discussion on the next topic under the broad series of lectures on fundamentals of geology. So, here we'll be now start our discussion on ductile structures, which is obviously a plastic response of the stress applied to an object. So, we have seen how an object might behave based on its inherent strength. If it's a stronger object, it will behave in a particular way. If it is relatively a weaker object, again that relates to its inherent strength, it will behave in different manner. And also there are the broad three responses. The first one is always elastic in nature. The second one could be plastic or brittle response in nature. So here, whenever we are talking about ductile structure, we are simply referring to the plastic response or plastic deformation, where you are applying stress to an object, it is storing the energy internally and deforms, and it will not restore back to its original shape and size. So it's a permanent kind of deformation. So again, there are several ductile structures that can be observed in the field, or rather in several or across scales, but the most important one is the occurrence of folds. So starting with the occurrence of folds are spectacular geological structures, and possibly that is or folds are the most conspicuous structures that you can appreciate in all scale across the globe. So they are seen obviously in layered rocks, and Hall in 1815 first used the word folds in connection to rock structure. So folds, if I define folds are wave-like structure formed as a result from deformation of any planar structure or any planar feature. So like I mentioned, folds can occur in various scale. Here also we can see a field photograph of a fold in a rock. There are thick layers which are folded in a particular manner. There are also thin layers which are also folded but in a little bit different manner. And here is the first few examples of experiment that was conducted by Hall, where he used layers of cloths as an analog to the natural layering of rocks, and then he simply you can say pushed the two sides of the box, and he generated folds or wave-like features within those cloth, which was used as an analog to your rock layers. But before looking at the fold and its geometry or its components, it is very necessary to understand that how folds form. So obviously, to start with, the first thing that if you want to appreciate a fold, or if you want to simply study a fold, you need to have certain kind of marker beds within it. So for example, again, if I take an igneous rock which is homogeneous in nature like that of granite, even if it is folded, you will not be able to identify or appreciate the structure, because the rock is mostly homogeneous in nature, at least in your outcrop scale or in your hand specimen scale. So you will not be able to see any kind of you can see disturbance in that particular rock. But if you have a certain kind of layering that is or that was already present in that rock, now if you are folding it, then that particular layer or bed might result into formation of these wave-like features. So these are the two examples where you have a homogeneous rock, you are shortening it, no folds will form in that. But if you have a layer which is not homogeneous, that is heterogeneous, there are some layers in it, then after shortening or after applying some stress, then these layers might get folded like this. There are various mechanisms of folding. Again, I'll not go into the very advanced discussion of the individual folding mechanisms, but just to have a look on it, you can fold a layer of a rock like this into this ways. You can either fold one part of it, you can fold both the part of the layer, or you can simply keep the hinge zone or the you can say the crust zone of the fold in static condition, and you are deforming the fold from the two sides. So there are various mechanisms. So the first one is your formation of buckle folds or buckling. Folds can also get created by simple bending. So if you have a, for example, wooden plank like this, and you are applying some kind of force or stress to it, then it might flexure a little bit. So if there is a flat wooden plank, you are applying some kind of stress, it might get folded like this. So that is simple example of bending of a layer. Then you can think of buckling, which is obviously again the most likely phenomena of the occurrence of a fold, that there is a layer, you are applying two forces from two sides or from the two ends. So what will happen, that layer will start to buckle, or that layer will form your wave like pattern. So in that progressive flexure, what will happen, there are zones. If there are multiple layers also, if there is a single layer, it will buckle on its own. If there are multiple layers, then what will happen, the layers that are present in the upper part of this crest and the lower part of this trough, this part can be considered as the crest, this part as can be considered as a trough. It's culminations and depression. So the upper part of this culmination will go into some kind of extension, because you are simply extending the material. Similarly, the lower part of the trough will also go into extension. But if I am looking at the central part or inner part of the culmination as well as the inner part of the depression, in that case there will be shortening, because you are shortening. So the material that is present on the upper part of my palm like this, then this part will go under stretching, this part will go under shortening. So likewise, again, in those parts, for a large scale fold, in those parts you will get again shortening structures as well as stretching related structures. Then there is another category of folds referred to as flexural folds, and it is also divided into two subcategories: flexural slip, when multiple strong slip layers of finite thickness, means known thickness, with low cohesive strain between the layers. And you also have flexural flow, the layer thickness is taken to be infinitesimally thin. That means it is, the layer thickness is so fine that you can't really separate the layers. So the whole layer, or the whole means you can say marker that is necessary to identify a fold, will behave in an uniform manner. But in case of flexural slip, there are continuous marker beds which are now means with response to the applied stress, it is you can say the slip is along these layers that are placed side by side. So there is a slip like this. So if I look at this in a enlarged form, you can see there is some slip between the two layers, and that is also can be quantified with the help of shear strain. I'll not go into details of the longitudinal or shear strain here. We will be just referring to the structures and how they look and what are the components. For this, you have an advanced level course also available in NPTEL by Professor Shantanu Mishra of IIT Kanpur. You can look at that course for the advanced level understanding of this particular mechanism, also the overall understanding of the subject structural geology. So here again, if I am coming back to this idea that flexural slip, so individual layers will go into right lateral and left lateral kind of slip, and they will form folds like this. You also have passive flow folding like this, when your layer is passively getting folded, and it is very common in kind of a fold that is formed or that is referred to as a tigmatic fold. So this passive flow folding of one particular layer can be considered as a tigmatic fold. Shear folds are nothing but, if you can again take a deck of cards like this and you apply, you have taken a deck of cards, you are applying certain stress from up or from bottom. So what is happening, that the deck of cards or the individual cards are sliding past one another. So what will happen, they will develop this movement of the cards overall will develop an wave like feature. Though the movement within the cuts will be obviously planar movements like this, that the movement will be mainly constrained across this plane or along this plane like this, on the left side as well as on the right side. But overall, this movement of the cards will give you an wave-like feature like this. So that is again categorized as shear folds. So now these are the different types of fold mechanism. Though I have again have not discussed that in detail at this fundamental level. Like I mentioned, for advanced level, you need to have a detailed understanding of the subject as a whole, structural geology. So here again, as we are only discussing the fundamental concepts, so here we'll look at the geometry of a fold again. So a fold have multiple components starting with the in layers. So these are the layers or markers that are defining the particular fold here. Then you have your fold axis, which is the zone of, you can say, the zone of culmination, which is also referred to as crest of a fold. But always crest and hinge zone are not same. Your hinge zone are the zones of maximum curvature in a fold. Similarly, the zone of minimum curvature is your inflection zone or inflection point. So a line that is present parallel to the hinge line or the hinge zone, and if I move that line, you can generate the whole fold like this, then that line will be considered as the fold axis. Then obviously, if your fold is now you have the fold already, so then you have three parts of the fold. Obviously, the top one or the crest or the trough one will be considered as the hinge zone. The rest of the part will be considered as the limb of the folds. Similarly, you have an arbitrary plane that is also used to identify several categories of fold, that is your axial plane. So it's a planar surface that goes through the hinge zone and will contain the fold axis or will contain the hinge line. So in that case, that planar surface, based on the how the planar surface is oriented in space, whether it is sloping in some direction or dipping in the other direction, in that case you can also classify folds based on the orientation or the geographical orientation of the axial plane, as well as based on the geographical orientation of the line in your the three-dimension orientation of the line as well as the three-dimension orientation of the plane will help you to classify fold into subcategories. So you have your these are the different components. Apart from that, there are angles like this. The angle formed by the tangents with respect to these limbs, and the tangents are drawn through the inflection point. The tangent will touch the limb at the inflection point. So if I draw two lines like this, so they will intersect at some place, and this will be the interlimb angle, means the angle between the two limbs will be treated as the interlimb angle. Apart from that, as fold are wave-like features, so definitely they will have certain wavelength, also they will have certain amplitude. So based on that also you can have an idea that this is the amplitude of a fold and this is the wavelength from one trough to another trough or from one crest to another crest is your wavelength. Similarly, your amplitude is this distance from inflection to your enveloping surface. Enveloping surface is again an imaginary plane about which there are two surfaces which are referred to as enveloping surface. Within that, your fold is constrained. So these are the two enveloping surface which is constraining the fold. Within this, again these are arbitrary planes, they are not means enveloping surface will not get a very distinct enveloping surface or plane and that is occurring naturally. So these are again your axial plane, your wavelengths, your amplitude, your enveloping surface, these all you can measure, but these are not, you can say, physical properties of that fold or the morphological feature of that fold. These are arbitrary planes or lines that are used to designate a particular type of fold. Based on this idea of the wave like or the components of the fold can be classified into various kinds. The first one, again, you have this wave like pattern, so you are getting a kind of a closure. So based on the direction of closure, folds can be assigned as the upward closure means antiform, downward closure means synform, and sidewise closure means neutral fold. So based on that, folds can be categorized into these three broad groups. Also, you have terms like anticline and syncline, but these are not structural terms. Remember, these are stratigraphic terms. Often people misuse this term in synonymous, and people think these are synonymous to means antiform and anticline are synonymous, syncline and synformal are synonymous, but they are not. Simply anticline and syncline, these are stratigraphic terms. That means they have an age connotation to it. So whenever we are saying anticline, that means you will have older rocks in the core of the fold and you have younger rocks towards the outside of the fold. Like if I take this example, I will say that the younging direction of this fold, if it is like this, that you have older rocks at the core, younger rocks outside, then this antiform will be categorized as antiformal anticline or anticlinal antiform. Similarly, if you have older rocks here and younger rocks outside like this, in that case they will be considered as your synformal and anticline. So in that case, based on this terminology and mix, you have antiformal and anticline, you have synformal syncline, you have antiformal syncline, also you have synformal anticline. So based on both the stratigraphic and the direction of closure, these four types of folds can be classified. Based on the profile plane, profile plane is also very important because it is nothing but a plane that is perpendicular to the fold axis. So the profile plane will give you actually the true profile or true geometry of a fold. So if there is a fold and if I am cutting it at an angle, you will not be able to appreciate its true nature or true profile. So that's why it is always considered that if there is a fold, this is your fold axis, then I will take a plane which is exactly orthogonal or perpendicular to this particular fold axis. So in that profile plane, we will do the rest of the measurement, be it the measurement of your wavelength, your amplitude, your interlimb angle, and so on and so forth. Based on that, also the other, you can say, morphological features are analyzed on the profile plane. Then you have another important component, that is Gaussian curvature. Gaussian curvature of a wave or a fold refers to that if the Gaussian curvature, that is the maximum curvature multiplied by the minimum curvature of a fold is 0, then I can treat it as a cylindrical fold. Otherwise, any other number you are getting, it has to be a non-cylindrical one. So a cylindrical fold, and the difference between a cylindrical and non-cylindrical fold is nothing but that a cylindrical fold having a straight fold axis, a non-cylindrical one will have a curved fold axis. So due to that, the Gaussian curvature, which is again in the multiplication of the maximum curvature, that can be recorded at the hinge point, as well as the minimum curvature that can be recorded at the inflection point. So based on this multiplication, if you are getting 0 as the result, so the Gaussian curvature of a cylindrical fold will be 0. Any other number will give you a non-cylindrical fold like this one. So here I can also say that your this thing is straight, the fold axis is straight, here the fold axis is curved in nature. Then based on the fold symmetry also, folds can be classified based on how the axial plane, again that arbitrary plane that divides or that passes through the hinge zone and contains the hinge line or the fold axis, will define the symmetry of a fold. So if you have axial plane that is symmetrically bisecting the two limbs or two parts of the fold as mirror image to one another like this, I can think of a plane going like this, there is a fold like this. So this will symmetrically bisect the fold into two halves. But if the fold is like this little bit, it is not a symmetrical one, it's an asymmetric one. So in that case, your axial plane will not bisect or not give you the mirror image of the other half of the fold. So based on that, fold can be also grouped into two broad classes, symmetrical and asymmetrical one. Based on the interlimb angle that is measured on the profile plane and the angle between the tangents drawn from the inflection point of the two limbs, fold can be again categorized under these categories. Your gentle fold, when the angle of or the interlimb angle is between 180 and 120 degree. Open fold, where your interlimb angle is between 120 to 70 degree, followed by close fold, when your interlimb angle is between 70 and 30 degree. Then you have tight fold when the interlimb angle is below 30 degree but little more than 5 degree. If it is below 5 degree till 0, then it is an isoclinal fold. And there are some fan folds as well, where you have negative interlimb angle, means now the interlimb angle will be subtended in the other direction, not in the direction we did earlier. So that's your classification of fold on the basis of interlimb angle. Then you can also have an idea about the dip of the axial plane based on the axial plane dip. Now if you have a plane, it will obviously slope in one direction or the other, otherwise it will remain vertical, or it might also be horizontal in nature. So if there is a fold like this, I'll say the axial plane is vertical in nature, that is upright. If it is sloping in some direction, we can see inclined fold. Then you can have overturned fold. Then also when the axial plane is becoming kind of horizontal, it will be considered as your recumbent fold. So it is simply a function of the dip of the axial plane, that whether you will categorize the fold under upright fold, inclined fold, overturned fold, or recumbent fold. And specifically in case of overturned fold, there is, why it is referred to as an overturned fold, because there is rotation of one of the limb more than 90 degrees involved in that. So that's why it is no longer a normal fold, it is now an overturned fold. So here is an example of a normal fold. Here if I say now this one, this is an example of an overturned fold, where your one of the limb has rotated more than 90 degree from its start of your deformation. Earlier there was layer which has been folded into a normal fold. So already you can see there is a rotation of about 40 degree, 60 degree, 70 degree, whatever it is. Now you are rotating it further. So finally, if the rotation exceeds the 90 degree angle from its initial stage where it was a horizontal or planar bed, in that case it will be considered under overturned fold. Based on fold harmony also, folds are categorized broadly into harmonic fold and disharmonic fold. The simple idea of harmonic and disharmonic fold is that if the axial plane of the subsequent layers that are folded together, if they are more or less they have parallel axial planes, in that case they will be considered as your or the continuous axial plane. If you are getting, in that case it will be considered as harmonic fold. In case when different layers have different axial planes, means folded layers have different axial planes, so the axial planes are discontinuous in nature, in that case they will be considered as disharmonic fold. So based on two parameters, again John Ramsay, who is also referred to as the father of structural geology, classified folds based on two parameters. The first one is the thickness of the fold. There are also two types of thickness. One thickness that is measured perpendicular between the layer, and there is a thickness which is measured parallel to the axial plane of the fold. And the other parameter, that is the dip isogon, that refers to the line of equal dip. So if a fold is there, at individual point there is a change in the slope from hinge zone to the inflection, where you have the maximum curvature, where you have the minimum curvature at the inflection zone or inflection point. So at each part of this limb, the curvature of the fold will change. So if there are two layers, for example, then I can have two places on the two layers where the dip of the limb is exactly same. So I can draw or connect these 2 points or 2 levels of same dip. So that will give you the dip isogon. So that is the line of equal dip. So based on this also, Ramsey proposed a classification of class 1A, 1B, 1C, that is one class, the other class 2, the third one is class 3, where simply by looking at the fold you can say, again if I look at the dip isogon, you can see for class, all the class 1A, 1B or 1C, you have a convergent dip isogon. So the dip isogon lines that join the point of equal dip are converging. Then you have class 2, you have the dip isogons are parallel, so they are also referred to as parallel folds. And the third one, where your dip isogon from one layer to another, they are diverging. So in that case, they will be considered as your divergent dip isogon or class 3 folds. Based on the dip of the axial plane and plunge of the fold axis, Flutie also proposed a classification scheme, and this is also very widely used. Apart from the Ramsey's classification, this classification is also very widely used based on the dip of the axial plane, in which direction your axial plane is sloping or dipping. Here I would like to mention a small thing, that for measurement of any kind of plane or line, you need to have an idea how they are set in the three-dimensional reference frame, or how they are set with respect to the geographic direction. So if there is a plane somewhere, I can think of a strike line like that will get generated by a horizontal plane which is cutting the plane, which is cutting this plane under consideration. So that line will give you a direction with respect to the geographic north. So I can also define in a way that strike line is nothing but the geographic orientation of the horizontal line on a plane. So if you simply assume an horizontal plane, it will cut this plane and will generate a horizontal line. So I will say specifically the strike is the geographic direction, because again we are referring it to the geographic north. So strike is the geographic direction of the horizontal line on this plane. So that's what strike is all about. And the slope of the plane, in which direction the plane is sloping, here in terms of rocks and planes, we will always say not slope, we will always say dip. So the dip of the plane is nothing but the slope of the plane measured perpendicular to the strike of the plane. So if this is the strike of a plane, you can think of a plane like this. This is the strike, that is the geographic orientation of the horizontal line on this plane. Then you will measure the slope of this bed perpendicular to it. So that will be considered as a dip from the horizontal. That means you will get an angle out of it, be it 20 degree, 40 degree. If it becomes vertical, it will be the dip of the plane will become 90 degree. If it is horizontal, that means the dip of the plane will be 0 degree. So like that, you will have the dip of the axial plane. So based on the dip of the axial plane, they are categorized as your upright fold, steeply inclined fold, moderately inclined fold, gently inclined fold, and recumbent fold. So you can also look at these diagrams to have an idea how your axial plane is oriented within the fold. Apart from that, there is another thing, that is the plunge of the fold axis. Again, it's a line, like we have seen that fold axis is a line. So again, you need to fix the three-dimensional orientation of this line in space. So that is done again. You can say the direction of this line with respect to the geographic north again will be the plunge direction of that line, and if that line is sloping in some direction, then I will say it is plunging in some direction. Then if a line is like this, then the direction of the line will be the horizontal line just above it in a particular direction, and this direction will be measured with respect to the geographic north. I can measure this. If again this is the line, I can take again this pen. I will say if this is the line, this is the strike of the line. Here I will not say strike, I will say the plunge direction of the line, and the angle between this horizontal and the line will be the plunge amount. So again, if I want to constrain the geometry of a fold axis, I need to find out the plunge amount, how much is it plunging, and in which direction it is plunging. So that direction will be obviously the horizontal direction, again because that is measured with respect to the geographic north. So in that case, I can also classify folds based on the plunge amount, and I will say that there are horizontal folds where your fold axis is horizontal, then you have gently plunging where your fold axis is gently plunging like this, you have moderately plunging a little bit more, you have steeply plunging, you have vertical. That means if I now look at the fold, then this is a gently or you can say horizontal plunging fold or horizontal fold, gently plunging, moderately plunging, steeply plunging and vertically plunging. So once it is coming into vertical plunging, it is also becoming a neutral fold based on the closure. Now you have a sidewise closure. So your neutral fold will or can be achieved from an upright antiform or an upright synform. If I rotate it, if I rotate the fold axis, the same antiform or synform might become a neutral fold. So, so based on the dip of the axial plane and plunge of the fold axis, this thing we can be categorized based on fold vergence as well. General vergence in which direction is fold is propagating, like this upright, inclined, overturned, recumbent and plunging fold. Folds can be classified into this fold based on the fold vergence as well. If there are more than two generations or even more generation of folds in a region, then your superposition of folds might take place, resulting into your complex geometry like this. Your this one is simply a dome basin kind of a structure. This one is a crescent shape kind of a fold. This one is a hook shape kind of fold. So these are much complex structures of fold, and that requires an advanced level of understanding. Like I mentioned, that if you want to have an advanced understanding of this subject in particular, you should take another NPTEL course by Professor Santur Mishra from IIT Kanpur. So that course is specifically designed for the discussion or the intricacies of the subject structure geology as a whole. But here I'll be only again discussing the fundamentals idea of the broad subject geology. Last but not the least, another ductile structure which is very important, like we have seen folds. Folds are purely compressional structures, whereas budinas are purely extensional features. There are instances where folds and budinas are present together, but again that is not a matter of discussion here. So budinas is a geological term for structure formed by pure extension. Budinas can develop broadly in two ways: planar fracturing into rectangular fragments like this photograph on the right hand side, and also by necking or tapering into elongate depression and swells like this photograph in the left hand side of your screen. So so if you are extending a layer again, so what will happen? It will try to stretch till its inherent strength is not exceeded. Once the inherent strength is exceeded, it will try or it will break up, but in a ductile fashion. It will not break like that of a joint or fault, that we'll be discussing in a bit. And budins also occur in all scale like that of fold. You can see large budins, pinch and swells in field. Also under microscope you can see like this. There are several types of budins: folded budins, shortened budins and sheared budins as well, which are also or which can be appreciated in extensional regimes as well. So these are the two main, obviously the first one, which is the dominant structure, you can say, across the globe, which is the most dominant ductile structure across the globe, that is your fold. And budins are not as conspicuous as that of fold, but they are, no, I'll not say very rare structure, but they are also present in abundance, you can say. So I'll end my discussion on the ductile structures here. Next we'll move to brittle structures. Thank you.